Okay, this was a phase diagram showing this notion of sensible and latent heat for water. So this is looking at water going from ice to steam. And this is looking at how the sensible temperature, the temperature you can sense on the y-axis, goes up as energy goes in. And this is not the rated energy, but the total energy. So as you add energy, you melt ice, it turns to ice and water. Then you get water, which the temperature increases from 0 to 100 degrees centigrade. And then it stays at 100 degrees. So you have feel with your and then, okay, videos I gave you. The basis for measurements. So we talked about absolute zero. So there's a reference point for temperature measurements in which there is no energy in the molecules. They do not move at all. There's no sort of this thermal vibrational energy, and they're actually in a crystalline state, so that there's no potential energy either. And this was a notion of what average temperature looks like. So it's a real important mental model to note that when you measure temperature, you're measuring the average temperature of the molecules, not the temperature of all the molecules. So there's high energy molecules and low energy molecules within a cup of water. If that were not the case, you would not get evaporation. So this shows you what happens when you increase temperature. You push this Gaussian distribution to the right, and you have more high energy molecules, and those high energy molecules have high enough energy to escape the clutches of their neighbors. Those viscous forces, those surface forces that we've talked about, the van der Waals forces, and they can escape into a gas phase. So going from red to blue is heating up a cup of water. It's not literally going from 70 degrees to 90 degrees. It's actually this movement of this average energy content of the molecules. Okay, an image of what molecules look like, and these are the surface forces that keep them together. So surface forces are really important in terms of understanding phase, and they're important in understanding viscosity too. So this is sort of a good mental image. Water is very polar. The hydrogen, the oxygen orientation, the angle of the hydrogen with respect to the oxygen gives a strong polar component that makes it sticky, makes it magnetic, makes water want to stick together and make raindrops and such. So it's an important constituent. So this is looking at vapor phase, how things, you get this equilibrium between vapor and liquid phase. Those high energy molecules go up in a vapor phase, and then as they cool down, they go back down into liquid phase. And if you have a closed system like you do here on the left with a stopper in it, you get a pressure developed, an equilibrium pressure. And if you change that pressure, you change the amount of molecules that go into vapor or liquid phase. So I can change phase by changing pressure. And that's, we see that with refrigeration, which I'm not going to look at now, but that's a neat way to look at it, how we can, in fact, we have in the past made refrigeration systems. I'd love to do that because it's really kind of neat, but that's the whole notion of changing temperature and pressure. So this was a HVAC system where we're looking at moving energy by using water. And what we'll do, I can promise this, I will promise it, in BIX 331, we'll go and look at a mechanical equipment room, just because I normally do that in this class, and kind of get a physical sense for how this energy is pushed around a building. Just as it's pushed around your body, it's the same sort of thing. We talked about this several times, the Cornell lake source cooling system that takes this cold water from the bottom of the lake, 39 to 41 degrees centigrade, runs it through these heat exchangers, low Reynolds heat exchangers, because the pumping energy is very high for this because you're dealing with a lot of water. So when you pump water, you're pumping it with electricity, and that comes from someplace that we'll talk about later, from power plants of different sorts. And then it runs through these heat exchangers, it chills the water, and that goes up to the campus, and it's run through these air handlers, these boxes with coils and fans in them that blow cool air. And by doing this, you replace electric chillers, and it uses less energy. This was a bit complex, but this was looking at how pressure changes phase again. And if you go from A to G, in this example, we talked about an ice skate where when you put your ice skate on ice at point A and you step on your ice skate, you increase the pressure. That little sharp edge increases the pressure, so you get a liquid film under your ice skate. You actually move from the solid to the liquid phase. All right. And these are the ideal gas law relationships. PV equals nRT. We talked about that and how pressure increases in a bike tire as it heats up and that sort of thing. It assumes non-interacting spheres, and that doesn't apply at high Mach speeds. So high velocity gases don't abide the ideal gas law directly. And then we have these three laws of thermodynamics. Energy is conserved, entropy increases, and this absolute zero reference point. So the first law we will look at again with the Bernoulli equation. That's the one that we deal with the most. And we also, when we look at combustion later, we'll look at the second law, entropy, because that becomes important too, that randomness increases. Okay, first law again, the change in heat is equal to the change in internal energy plus kinetic energy plus potential energy plus work. And we're excluding nuclear reactions, but this is how this all works. And again, typically what we're doing, if you're dealing with an adiabatic system where you're not adding or taking away heat, you're moving velocity and pressure. That's what we talked about with the Bernoulli equation. We're moving those back and forth. Now, of course, we can put a pump in a system and add energy. We can put a turbine in a system and extract energy. We can add a flame and add heat. We can do things to modify this, but these are always the governing relationships. Okay, just some pictures. Bernoulli, which we just looked at recently, so I don't want to belabor that. But that's turning the high velocity air into low pressure air, which causes an upward lift. And then the bottom view is a Venturi, where you're taking low velocity air, turning it into high velocity, and again, making low pressure. So it's the same sort of thing as the wing. One is sort of a flow over a plate, the other one's flow in a duct or a pipe. This is a Bernoulli equation. And again, the rho GH terms is when you're looking at gravity head, the difference in heights of fluids, which you often don't have to worry about. So you have pressure plus velocity squared equals pressure plus velocity squared. That's a simplified form of that. Okay, and these are just examples of adding internal and external energy. And this was, looking at energy movement and the human body, which creates heat through metabolic processes. And I now want to go to heat transfer. Okay, heat transfer. And remember, these are all kind of the thermal sciences. They do interrelate with each other, but fluid dynamics also has the element of drag that's important in design. So heat transfer, conduction, convection, radiation, these are means by which energy is transferred, and we'll elaborate on those. And then we have these other two, mass transport and heat creation, which are two different animals. They're they're not movement of energy alone. The first case is the movement of matter. It's opening a door and letting cold air in, or a bucket of cold air or hot air. This is physical movement of matter. And then heat creation or extraction is a process in which you have a fire. You're burning something, or there's a exothermic reaction occurring where heat is produced, or an endothermic reaction occurring where heat is absorbed. Something is chemically going on that's creating or eliminating heat. Okay, so you're not adding matter. So if I have if I start burning the carpet in my office, I'm not adding matter, but I am creating heat energy. Okay, which is different than bringing in a bucket of hot air. All right. And again, we've kind of looked at this a lot, so I'm going to go quickly and just want to give an overview of things. So heat storage is important. So within heat transfer, we think about storing heat because it has a lot of practical implications, not only for green building design, but also product design. And there's two elements to that. I'll go in reverse. So there's the mass of it, how much material you're dealing with, because you can have all these cool properties of solar gain and whatever, but if you only have a gram of it, it's not going to make much of a difference. Then you have specific heat, which is how a material responds to energy. So if something has a high specific heat, it takes a lot of energy to raise the temperature, like water. If it has a low specific heat, like air, or metal, it doesn't take much energy to raise the temperature. So that can be good. You know, it's if you're trying to heat something up quickly, you want low specific heat because it doesn't take much energy. If you want to store energy, you want low specific heat because you want to, in a practical sense, you don't want to have to insulate something that's 10,000 degrees. You want to insulate something that's 200 degrees if they have the same amount of energy. So specific heat has practical implications that way. I talked about hot water heaters. If you had a hot air heater, it would have to be volumetrically huge, or you'd have to make the air temperature really, 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 really hot. And that delta T then that you're worried about for conduction is such that you'd have to insulate the thing really well. Okay, and then we talked about why things feel hot and cold. So we talked about conduction, thermal conduction. And we looked at the bioclimatic chart, which was in the reading, which is looking at this balance between solar radiation or some kind of infrared radiation, wind, humidity, these kind of things. So we have a certain temperature range that we're comfortable with, but we can moderate that with radiation and wind, for example. So this is a radiant heater, an infrared radiant heater. And we looked at these kind of radiation properties. So here you're looking at absorption based on color. And this is absorptivity and reflectivity of different materials. So here you remember that there's that when something is irradiated, say by the sun, but it could be irradiated by a UV light, it could be irradiated by the wall of your room. It can respond in three ways. It gets absorbed, it gets transmitted through, or it gets reflected. Those are the three choices it has. If it's opaque, the transmissivity is 0. It doesn't go through. If it's a perfect black body radiator, 100% of the energy is absorbed, none of it's reflected. If it's a perfect reflector, none of it gets absorbed, 100% gets reflected. And then if that object, say you, are above absolute 0, you are emitting radiation too. You're emitting radiation. And your emissivity, your propensity to emit, is the same as your absorptivity. So what's called a perfect black body absorbs 100% of the energy coming at it, and it emits 100% of the energy coming from it. And I can change that by painting it. That's all it takes. Go to paint. Or some other, aluminum is a good example we talked about because it works so well in the UV spectrum. Okay, this is, we talked about, we had a whole lecture on electromagnetic radiation, but this was, just a refresher to remind us that there happens to be a range within the spectrum that the photoreceptors in our eyes respond to. Visible light, we call it, very important. And that's interesting. But here in heat transfer, we're more interested in the infrared part, which is the lower energy, longer wavelength, lower frequency. And you remember, frequency is a measure of energy. It's, times Planck's constant equals energy. So anyway, we respond to infrared as heat energy, and UV is above violet, and that's and UVC is used to decontaminate things, which is a bit in the news. It always has been, but a bit in the news now too. So if you want to clean things, to kill things, you use high energy ultraviolet light. Okay. And this happens to be green. So here we're looking at the absorptivity of green. So green, of chlorophyll anyway. So green has very low, chlorophyll has very low absorptivity at the green spectrum, green, yellow, orange even. And here, maybe you're thinking of this, even though it's in the morning, low absorptivity means high reflectivity. Has to be. As long as something's opaque, there's no transmissivity. If it has low absorptivity, it has to have high reflectivity. There's no other choice. Which means these look green. That's what it means. So the opposite plot of this, if I looked at reflectivity, would be the inverse of this. And the green would be way up here, and the red and the blue would be way down here. Okay, and this we looked at interesting stuff. So when the sun irradiates the Earth, it's irradiating physical things. The photons hit something. They can hit clouds, they can hit the few air molecules are out there, but they certainly smack right into the Earth's surface. So the Earth's surface becomes really important as far as handling solar energy. I mean, clouds do as well, but then remember the Earth is above absolute zero, which means it has to emit. It has no choice. It has to emit. So it emits to outer space. It emits to the clouds. It just goes out. But of course, the sun wins the battle because the sun's hotter. But when the sun's gone, outer space wins well, I guess the Earth wins the battle. We send our energy to outer space. Usually, we have water molecules in the atmosphere and we have clouds and things that kind of cut back that loss. And then, we talked about the condensing of water at the what's called wet bulb temperature. And once you start condensing water, you basically put the brakes on the night temperature, because if you remember that phase diagram, you start the latent energy changes, but the sensible energy doesn't once you start condensing water. Okay, this is looking, different spectra. And I talked a bit about snow, because snow is unusual in that it reflects visible light, but it doesn't reflect infrared light. So I won't belabor that right now, but snow is just kind of unique. And you see the drop off of snow at the infrared frequencies. Okay, this was looking at the building of, example, and we spent a good amount of time on this. So here's a horizontal surface, which means the roof. And the peak temperature of the roof is, say, around 2 o'clock, 1400 hours. And that's because even though the solar energy is at a maximum at noon, you can see my mouse over here, the outside temperature, this big fat line, doesn't peak until about 3 o'clock. So the temperature of the roof is a mixture of the outside air temperature and the solar radiation. That's what happens. And so there's a lot of information in this diagram. Now this is for a light colored roof. And as I flip to the dark colored roof, you're looking at the effect of absorptivity. So the light colored roof has low absorptivity, and you see this, what's called often cooling low temperature difference, CLTD, is 120 degrees. It's very high. And if I go, I don't have a dark colored roof here. Where is it? Oh, I don't know what I did with it. Okay, well, it's higher. It's a lot higher. It's about 40 degrees higher. When it's same thing, everything's exaggerated. And this is one way that it's handled, especially in the South. For commercial buildings, it should be everywhere. It's simply a surface treatment of the roof. You wouldn't want to do this in a residential home in northern latitudes, because heating is a bigger issue for many of us than cooling. We spend more money or more energy on heating than cooling. But in the South, that's not the case. And for commercial buildings, that's generally not the case. You're almost always cooling a commercial building, even at our latitude. Okay, this is an example of a friend of mine's wife with a white towel on her hijab here to reduce absorptivity. And we talked about how you could use mica and some other materials to keep the black color and reduce absorptivity. This is in the reading, or we've talked about it anyway at length, about the SR-71, where the reason it's painted black, which added a couple hundred pounds of weight to the airplane because of the weight of the paint. What it's doing is it's emitting radiation. So this gets really hot as it travels through the air, but the air is very thin, so the convective heat transfer to the air is very low. There's no conductive heat transfer because the air density is so low. There's no mass transport. I mean, it could carry tons of water and jettison it and just kind of get rid of it that way, I suppose, but that's not practical because of the weight. And there's no endothermic reaction like a cooling gel in there because, again, you have a weight issue. So the only way the best way it can get rid of energy is through convection and radiation. And again, convection doesn't work very well, even though it's traveling fast. So that convective heat coefficient is really high, but the density is really low. So there's not much media to work with. There's not much air to work with. So it relies on radiation. And it has emissivity to work with. And to improve emissivity, you paint things black. That increases emissivity. So when the sun's out, black is bad, and this photo was taken in the sun, but only in the direction of the sun is that bad. Towards the earth and elsewhere, it's good. And of course, when the sun's at low angles and such, then the emissivity of the airplane always wins. So I guess if I don't know actually how this would work out. If the sun is directly overhead of the airplane, for those few moments it's directly over the head, maybe black is worse, I don't know. I mean, the bottom of the plane is still emitting, but the top of the plane is absorbing more than you'd like. But of course, how often is the sun directly over the airplane? Okay, seatbelt buckle, we talked about that. That was the issue related to specific heat. So even though the metal absorbs less heat because it's reflective and the webbing is black, the specific heat is low, so the little bit of heat that it does absorb makes the temperature go way up. Also, when you touch it, so there's kind of two parts to this. The thermal conductivity of the metal is very high, so all that energy flows right into you, whereas the webbing is an insulator. So when you touch it, the heat does not race to burn your finger. Okay, and then we kind of looked at that. And okay, this was looking at mass transport. So if you can sweat or breathe, do heavy air breathing or heavy breathing, and you dispel a lot of the moisture in your body, you're getting rid of a lot of energy. So sweating and breathing are a good way to get rid of heat energy, which is used, in many animals. And here we talked about, some of the other animals and plants that use different features to get rid of heat or improve heat, either get rid of heat or gain heat. There's an equation for radiation. And we'll go to, how are we doing time? Okay, we're doing all right. We'll go to heat transfer, which you just saw, or I'm sorry, fluid dynamics, which you just saw. And here we talked about fluid statics and fluid dynamics. Fluid statics is fluids at rest, which is, in practical sense, is used for, in my world anyway, conveying power, torque especially. A lot of twisting action in hydraulics and pneumatics. I mean, it's power too, which is just the rate of applying torque. So hydraulic and pneumatic systems. We talked about pneumatics, whether it was just air or not, and I'll say it is. And anything else has a specific name. So whether it's compressed natural gas or nitrogen systems or whatever, that's normally what we call them. So pneumatics are open-ended. You vent the air when you're done. Hydraulics, you have to return the fluid back. Okay, and then why are we interested in fluid dynamics? Drag is a big part of it, reducing drag, and that's good for a lot of things. Usually, except for parachutes and things like that, we were trying to increase drag. So there is a case where you might want to increase drag, braking, that sort of thing. And then also control issues. And fluid dynamics does relate, of course, to heat transfer too. So drag, we have a couple of elements to that. We have these three: friction, pressure, wave making. Again, wave making was lifting a fluid up against gravity, so it uses energy. Friction is the measure of resistance to flow as a function of velocity and the roughness of the material, and then pressure is a function of the velocity and the shape of the material or the form of the material. And there we're looking at coefficients of drag, for example. We're looking at high pressure and low pressure parts of the shape, like you see with this round cross-section area where you have this impingement pressure up in the front and this low pressure area in the back. That's an example of pressure drag. So it's usually the dominating drag on objects at any kind of reasonable speed. So here we're looking at wave-making energy, wave-making drag even. This is a Moody diagram, which we talked about, and here you can see the Reynolds number in the x-axis, where you have two domains, laminar and turbulent, which we talked a lot about, and because it's a little bit fussy, but that's what we talked about. The friction factor is multiplied by the velocity squared. So Reynolds number means things are going faster. Friction factor is affected by the roughness of the pipe for turbulent flow. For laminar, for laminar flow, it's really not, but as you can see. But again, you are multiplying by velocity squared. And this is an example of pressure drag, and based on shape, which we talked a lot about, some visuals. I also have the PowerPoint and the video on computational fluid dynamics you can look at just to get more visual sense for this sort of thing, because these are cross sections of bike frames. So you can, I mean, this is really important stuff, like we talked about with the Brazilian shoe problem, whereby a, s- a small weight addition, maybe no weight addition, some small changes to volume, you can reduce drag, which is a good thing. And with modern manufacturing, like injection molding specifically, you no longer need simple shapes. You can deal with complex shapes. This is a really helpful diagram. You can spend some time with this and dissect this. The right one down here is looking at ship drag. So it's got a big wave drag component where you're lifting water up. The right diagram is looking at pressure and friction drag and total drag and optimizing that. It's got the coefficient of drag equation in it with the V squared term. So if you're solving for F sub V, the friction or the force caused by drag, it's the coefficient of the drag coefficient times the velocity squared times rho LD and all that. And I've got in the book, I've got some coefficients of drag in there. So it's based on shape, and you're experts in shape. So if you're trying to reduce drag, you want a low drag coefficient and you want a low velocity. That's always good, I'll say. Okay, and then we talk about viscosity and how it's affected by temperature, how you have this section, this discharge area that is for fans, where the viscous forces draw all the molecules to the same velocity, and you get what's called fully developed flow, which has this profile that you have on the outside here. And this was looking at pressure drag, and then yeah, laminar and turbulent flow. And here you see the transition from laminar to turbulent. There's a time domain there. So when we look at the flow over a plate, you'll see that again. So laminar and turbulent flow, which we spend a lot of time with. This is a good diagram. This is a flow over a flat plate. So it's sort of like the smoke stream that you just saw. When you initiate flow, you do get a laminar portion of it. And then if it's at a high Reynolds number, over 2000 at least, it will trip to a turbulent boundary layer, but it does take some time to do that. If it's a low Reynolds number or low flow, you'll have a laminar flow throughout. And you remember a turbulent boundary layer has a thinner low velocity section to it. A thinner low velocity section. That's the important part. Even though the actual boundary layer, turbulent boundary layer is thicker, just think of it as being thinner low velocity section. And by having a thinner low velocity section, it means you get better heat transfer because it's a thinner low velocity section, and more stickiness. It will follow the curvature of surfaces better. So if you want to trip something to turbulent boundary layer faster, you put turbulators or roughness at the leading edge of it to essentially get rid of this short laminar portion. And we looked at that with the bowling ball. So, and yeah, okay, some more examples. And here you see velocity. Here's a velocity profile of laminar versus turbulent boundary layers. And I don't mean to get all hung up about the laminar and turbulent boundary layer, but it's again, it's a designer's issue, because I guess I'll say, yeah, generally you want a turbulent boundary layer. That usually, if you're at high Reynolds number, if you're a low Reynolds number, you're never going to get you're not going to get a turbulent boundary layer anyway. So if something's going very slow, you don't want to have turbulators or rough up the bowling ball or any of that stuff, because all that does is add friction drag. But if you're going at Reynolds number over 2000, you want that. Now I'm going to run out of time here soon, so I'm kind of going to try to go promptly here. I can't see the clock on this, so if we drop out, oh yeah, no I can't. Okay, good, 5 minutes. Okay, so here is a bowling ball example that you've seen. So with the roughened edge here, and this has the bowling ball on the right has a lower pressure drag than the one on the left. Even though they're going at the same velocity, the water has the same rheological properties on both, or the fluids are the same fluids, same rheological properties. And the golf ball, which we talked about, you got this counter-rotating portion. And then terms, which let's see, well, we'll shoot through these. Viscosity is resistance to flow. And we talked about how actually there's a shear component, a shearing force on the surface of the plate when the fluid goes over it. And that shearing stress, I should say, shearing stress times the area gives you the drag. So that's a calculus concept, because you take the shear stress times the differential element that it's working over, and you can add that over a whole surface, and that gives you total drag. So viscosity is resistance to drag, resistance to shear force. Compressible, There's compressible fluids and compressible flow, so I don't want to mix those up, which is kind of interesting. But we'll say compressible fluids are fluids that where the density varies and or can vary, like gases, and specifically low Mach gases. Incompressible, the density won't vary. So if I push on one end of a water tank, the pressure gets transmitted universally through the whole thing. I can't have one area of locally different density in an incompressible fluid. And that's a lot of words, meaning it doesn't compress, but I hope that makes sense. High Mach gases act like incompressible fluids. They are, in fact, incompressible fluids. Okay, Reynolds, I've got some slides on these, so we'll look at those later. Okay, and then drag, we talked about Bernoulli. We just talked about, so I won't talk about this again. You can use that simulator to put an airfoil in and look at temperatures or densities and velocities around the airfoil or whatever other shape you draw to kind of get a sense for that. Okay, but real practical, I can make a vacuum cleaner with a shape. I can make a wing with a shape. And you're experts on shape. Coanda effect, we talked about the low pressure section between a wall and an airstream that draws the air to the wall, and it can be used in a practical sense to transmit air, especially or some fluid over a distance. Okay, and these are just some examples of ducts. Oh wow, I got 2 minutes, 56 seconds. Okay, just some formulas for working with actual practical heat loss. And okay. This is pipe cost, which is a practical thing. These are just some real examples of what you do with information. So you measure things and you get equations. You do curve fits, and Excel does that for you. You can get curve fits from Excel. It's free, and do cool things with it. Okay, rheology. The first question you ask when you're dealing with a fluid dynamics problem, which includes convective heat transfer, by the way, is what are the rheological properties of the fluid? That's the first question you ask. And basically you're saying is it Newtonian or non-Newtonian, and then you ask about viscosity, you can ask about specific heat and all these kind of things. But the rheology means that, you know what, these properties that we think we know change with pump speed or shear rate. They change. And we're not used to that. That's unusual. So with molasses and paint and things like that, you know, the rules change. And blood is, again, using the fluids I have up here, air, water, oil, and blood. Blood is the one that acts that way. And but there's others too. So I don't know what business you'd be involved with. Okay, and then, you know, we're worried about dynamic or absolute viscosity. Forget about kinematic viscosity. And okay, water is good. Blood is good, but it acts funky. And okay, and okay, Weber. Oh yeah, Weber number. Weber number is surface inertia over surface tension or velocity over surface tension for atomizing. Mach number is speed of an object over the speed of sound, and Reynolds number is the velocity over the viscosity, or technically the inertia over the viscosity.